This problem has us find the closed form solution for theta of t in this given situation. So to get to theta of t, we're going to need to start with our standard procedure, and that's going to start with a model of our system. So we are presented this situation here with our system in equilibrium. We are going to be ignoring the mass and inertia of the rigid bar, so we can ignore this part in this problem. We'll get to dealing with masses later. So we have a forcing function acting on that heavy mass at the end that we're going to need to account for. But first, I'm going to draw the system in its equilibrium position and then in a perturbed position. And here we want everything in terms of theta ultimately, and we're being told that theta is going to be measured as a clockwise rotation. So I'll stick with that notation. All right, so we have a spring K1, a spring K2, A and B and L happening here. So A is going to be this distance, B is going to be this distance, and L is the full distance. And I'm going to choose my degrees of freedom to match the positive direction of theta, just to make this a little bit easier. So the amount that the end of K1 moves, I'll call X1, and X2 for K2, and I will call this X, the vertical translation of the heavy mass at the end. All right, so we are going to be assuming, once again, small angles of deflection. So X1, X2, and X will be purely vertical. And we'll be able to use a similar triangle relationship to relate theta to X1, X2, and X as we go through. Let's start forming our energies. I'll start with the kinetic energy. Will be a little bit more straightforward because the only thing that will have kinetic energy is the point mass at the end, m. We are ignoring, again, the mass of the bar itself, and the springs have no mass. So only one term will have translational kinetic energy. Since we are assuming small angles of deflection, we're going to assume that m travels only vertically. So 1/2 m x dot squared. And our potential energy, we have K1 and K2 are springs. They will have spring potential energy. As normal, we're going to ignore gravitational potential energy of m and the bar, even though the bar is massless and inertialess anyway. So the only thing that could have potential energy other than that would be the bar itself, but we are told to treat it as a rigid bar, meaning that it does not deflect, so it's not going to store potential energy. So the only things we need to count the potential energy of are the springs. So we have a 1/2 K1 x1 squared and a 1/2 K2 x2 squared. Now we want to remember, what are we trying to ultimately find in this problem? I do want to make sure I make that clear as to the path we want to take here. We want theta of t. So we want the angle as a function of time. So if we look at t and we look at v, we have an x in t, we have an x1 and an x2 in v, but we want to get to theta. Now let's get some coordinate relationships here. Using the small angle approximation, we can say that theta is going to be x1 over a. We can say that theta is going to be x2 over b. And we can say theta is going to be x over l. So again, these are coming from, we could call it a tangent relationship, that the tangent of theta is opposite x1 over adjacent a. And using small angle identity, the tangent of theta will go to theta for small values of theta. Same idea for the second relationship and the third relationship. So there's going to be two ways we could go into the equation of motion step. One way will be to have everything in terms of that desired degree of freedom, theta. Now, an issue here with going right to theta is that we have to realize that this forcing is being applied on the degree of freedom x, not on theta directly. If this were a moment, then we could say it's affecting theta. So what we have to think about is when we go to make our Lagrange equation, that forcing function we're going to see on the right-hand side has to relate to the degree of freedom that is on the left-hand side. Now, this was not an issue in free vibration because there was no forcing, so it didn't really matter what degree of freedom we used. So instead of using theta as our degree of freedom right now, we could actually use the degree of freedom that the forcing is attached to, x, and make our equation of motion in terms of x. And then at the end, after we solve for x of t, we can then easily find theta of t, because we already know the relationship between x and theta. We know that theta is x over L. So we could do everything in terms of x where f is being applied, or we could do everything in terms of theta, and then we don't have to make that change at the end. I want to actually present this one both ways. And we'll see that we actually get to the same answer. It just depends on when we do this coordinate transformation. So I'm going to do this one the first way by starting actually with x of t, solving everything that way, and then with our result for x of t, we can get our theta of t. So what this is going to require us to do is get everything, all of our coordinates, actually in terms of x, not in terms of theta. So for this, we can use similar triangles. So I want another, these are just the same conversions really. X1 over a equals x over L. Really, we know that's true because the thetas are equal to each other. So we know that x1 is just going to be a over L times x. x2 will be b over L times x. Now I can convert everything in terms of x. So now t is okay, we have an x dot. So v is going to have to be changed. I have a 1/2 k1. x1 is going to be an a over L quantity squared, now x squared. 1/2 k2, and I have a b over L squared, x squared. And I'll rewrite this by factoring out my 1/2. k1 a over L squared plus k2 b over L squared, and my x2 on the outside there. And in this system, we are not going to have any dissipation. We have no dampers. We're not accounting for air resistance. And because the bar is rigid, it's not going to dissipate energy as it flexes. And even if it were deformable, we would probably not be accounting for that dissipation anyway. That's typically going to be more difficult to do and introduce nonlinearity into our system. So there's no Rayleigh dissipation in this one. So we can go to our equation of motion. Right? Again, we are going to do things in terms of x at the moment. So we will use, I'll put the Lagrange equation here. So dt del x dot plus del v del x equals, so again, x is my degree of freedom that I am working with for right now. And we see that on x over here, that is where our force is acting, this F naught sine omega t. And what I'm going to do, and we'll see why this is important when we redo this, is I'm going to put this delta x at the end to remind me that this force is acting on the x degree of freedom. Now, it's going to go away. It's kind of just there as a reminder. But what we need to have happen is that this delta x is going to match the degree of freedom on the left-hand side. So when we do this the other way, that's going to make a difference. So those match, so we're okay. So we really don't even have to worry about it. So I'll just cross it out because it's not going to have really an effect in this version of the problem, but it will in the second version. Okay, so now we're good. We have our right-hand side, that's the forcing. And now we can do our differentiation, and we are going to get an mx double dot plus del v del x is k1 a over L quantity squared plus k2 b over L squared x equals F naught sine omega t. And now I will put in some numeric values so it's easier going forward to do some of these calculations. So we were given that big M was 50. And our K equivalent, we get 1563 x equals F naught was given to be 500. Go back up here. 500 And our omega here is 1,000 RPM. But we do want to make a conversion here, so that's rotations per minute. But we want to be in radians per second. So one rotation is going to be 2 pi radians, and 1 minute is going to be 60 seconds. So if we do our conversion, this gives us a driving frequency in radians per second of 105. So we want to make sure we're in the correct units. So sine 105 t. So we have our equation of motion algebraically. We have our equation of motion also done numerically, which is where we can proceed with. But before we proceed, we need to identify the type of system that we are dealing with. So in our identify step, we are going to look at our left-hand side. We have an x and an x double dot. So x is our only dependent variable, 1 degree of freedom. No x dot term, so it's going to be undamped. Looking at the right-hand side, we do have forcing, so it is a forced system, and it's going to be simple harmonic, sinusoidal, which will make a difference, forcing. And the left-hand side, it is linear, which we want to make sure that we have. And also actually important here is that we are told that the system begins at equilibrium. So that means that our initial conditions are going to be 0. And that will actually be, so 0 ICs. That does make a difference in the identify step because we actually will have a simplified version of our solution or of our closed form solution when we have 0 ICs. All right, so we are undamped, 1 degree of freedom, forced system, simple harmonic, sine is the simple harmonic, linear with 0 initial conditions. So we can see what is our closed form solution going to look like. And looking at our pre-made solution, we can use actually the bottom for x of t because we are starting with 0 initial conditions. So starting from rest, 0 initial conditions, that's going to be our closed form solution to our x of t here. So x of t, our current degree of freedom we're working with is going to be this x times sine omega t minus omega over omega n sine omega n t. So now we can start looking at parameters because we need to know x. We actually know omega, that's the driving frequency, and we need to know the natural frequency. All right, natural frequency is going to be the same as it always is for 1 degree of freedom, root k over m. So that's going to be root of 1563 over 50, and that gives us a natural frequency of 5.59 radians per second. So the second thing we need is going to be the value of x. That is coming from that pre-made solution. There's different forms of it. I'm going to use this f naught over k over 1 minus quantity omega over omega n squared. So filling in the things we know, f naught is going to be the coefficient in front of the sine term. That is 500, is in base units here. Our k is 1563, and that's going to be 1 minus, our driving frequency is 105 over our natural frequency we just found was 5.59 squared. And when we do the arithmetic, we are going to get an x value of a negative 9.15 times 10 to the negative 4 meters. Again, we're working all in base units here, radians per second for our omegas. Our force is going to be in newtons, and our k is going to be in newtons per meter. So all of this will work out. So x is in meters. So we have our x, we have our natural frequency, and we were provided our driving frequency. We actually don't need our initial condition step because everything was starting at 0. So finally, we can assemble our solution. So putting this together, we're going to get here x of t is negative 9.15 times 10 to the negative 4 times sine of omega t, that was 105, times t, minus omega over omega n, is going to give us 18.8 times the sine of our natural frequency times time. And that will be in meters. So I did outline that, but actually we're not done yet, because remember, what do we actually care about is not x of t, we want theta of t. Well, now we can go and relate theta to x, because we have this relationship that we want to use here, that theta is x over L. So if we have x, we can divide it by L, and now we have theta. So there's actually one more step to this, is we want theta equals x over t over L. And this is also going to be a theta of t. Now, this one's kind of trivial because L was given to us to be 1, but still technically we are dividing everything by L. So we're going to be left with 9.15 times 10 to the negative 4. It actually doesn't change anything except the unit that we're in. This would be more interesting if the length were not 1. And this will actually be in radians because we're in meters and we're dividing by meters, which is unitless, but we're going to get our result here in radians. And this really is the answer we're interested in. So I'm going to get rid of this. And this is truly what we wanted from the start, was theta of t. Now, before we plot this and see what's going on, I want to look at an alternate way we could have solved this, which was instead of using x as our degree of freedom at the equation of motion step, we could have right away gone to theta, but we just have to be a little bit careful up front, so we don't have to convert at the end like we just did. We'll do slightly different. So going all the way back to our modeling step, we can make a different choice. We can put everything here now in terms of theta. So now the t, we will need to convert. We're going to need to have everything in terms of theta. So it's going to be 1/2 m. And now x is going to be, well, we need to rearrange it here. X is theta times L. So we're going to have an L squared theta squared. And for our v, each of these also needs to be converted. So I can express it in the other direction, just like I did for x. I can say x1 is a theta and x2 is b theta. So this will become 1/2 k1 a squared theta squared plus 1/2 k2 b squared theta squared. And now factoring out that 1/2, and I'll be left with a k1 a squared plus k2 b squared theta squared. Now, everything's in terms of theta, still no Rayleigh dissipation, that's going to look the same. Now I can write my equation of motion. So I can still use the Lagrange equation. So del t del theta dot, since theta is now the degree of freedom I'm going to be working with, plus del v del theta equals, and now my right-hand side. This is where I'm going to start with the same, f naught sine omega t. But remember, like I did before, this is acting on the x degree of freedom, not theta. So what I actually do want to do here is I can resolve my left-hand side. And it's going to be then the ml squared theta double dot plus k1 a squared plus k2 b squared theta. And what I want to do here is I can replace this delta x, again using this conversion that x is going to be L delta theta. so now my right-hand side has this delta theta. The theta is going to match what I'm differentiating with respect to on the left-hand side. So what happened is this extra L popped out from doing that conversion. So I can write now my right-hand side as F naught L sine omega t. And now I have my equation of motion, but it's in terms of theta. And we can see that the M equivalent is actually different than it was when it was x, and so is the K equivalent. And that's going to happen. The equivalent mass and the equivalent spring constant are going to be related to what degree of freedom we're talking about. Now again, looking forward and ahead, because L was 1, we're actually not going to see that much of a difference here. But since we're working with just algebra at the moment, they are different. And L could be any value. If L were not 1, we would definitely see a different MEQ and a different KEQ for this. But we're going to see some things don't change in the next steps. When we identify, actually nothing changes at all because it's still, the main system is identical to what we had before. So we know that theta of t, the only thing that changes is the variable we're using now is theta of t is going to be x sine omega t minus omega over omega n sine omega n t. And now we would calculate our parameters, just like we did the first time we went through this. So our natural frequency is going to be, again, root k over m. And we're going to have our k is k1a squared plus k2b squared over ml squared. And actually, when we do our calculations here, it turns out, because L is 1, that actually the numerical values of MEQ and KEQ are the same as they were the first time. But I want to point out that actually the natural frequency is the same no matter what degree of freedom we are working with. So it does turn out L is equal to 1, so it simplifies down. But even if L is not 1, our natural frequency is not affected by a change of coordinates. If we did this in x, x1, x2, theta, the natural frequency would always be the same, of 5.59. So that did not change. Our calculation of x will change slightly, however. We still are going to use this generic f naught over k over 1 minus omega over omega n squared. But when we go to put in the f naught, it's always defined as the coefficient in front of the sine or the cosine. So actually this is going to be our f naught. So it's going to be, I'll do it algebraically for right now, it's actually f naught times L over this k1a squared plus k2b squared over 1 minus omega over omega n squared. Now, it does turn out to actually still be the same value we got the last time, negative 9.15 times 10 to the negative 4, but now we're in radians. So again, I'll point out it's less interesting because L is equal to 1, but notice the differences here is that L on top, because the coefficient in front of sine has an f naught times L, and our k is different because that L squared in the denominator went away. So we have our x, we have our omega n. Now we can get to our theta of t. We're going to not quite see what's happening the same way we did before, but when we piece this together, we actually get the same result that we had the previous time, where we started with x and then converted it to theta. So sine 105t minus 18.8 sine 5.59t radians. Right, so numerically, we get the exact same result that we had when we initially had our equation of motion in terms of x rather than in terms of theta. So doing the conversion up front, we get the same result here. Even though we can't see that the L had any effect, it actually did. This is 1 over L, still 1 over L times x. It just happens that L is equal to 1. But we can see that what we did have to do is on that right-hand side, that forcing, because it's acting on the x degree of freedom, we had to translate it to its effect on theta, which is effectively what's the moment that this force is producing around the hinge is really what we were finding here. But we could do that coordinate transformation from this delta x to this L times delta theta. So that little delta on the right-hand side is just to keep track of what degree of freedom is the forcing acting on so that it is matching the degree of freedom that we are differentiating with respect to. So either way we go, we get the same result, just two different ways. With this, we can take it into MATLAB and see what the results are, because again, either way we did it, this is the same theta of t. In MATLAB, I'm putting in all my parameter values that we were given, and this is actually going to follow the first method where the equation of motion was made with respect to x and then converted to theta. And that really is only reflected here in 100 and 101, where I define x and then I'm going to define theta, the th value, with respect to x. But all these other calculations I'm doing here are the same as what I did by hand. So I will, up to this point, I will define x and theta. Now I'm going to do this for 2 seconds, and I'll define my t in time steps of 0.01 seconds. Because like the previous example, I want to plot my results and then I'll go backwards, look at the power spectral density, and make sure that from analyzing the data, I could reconstruct my original signal, or at least know what the strong frequencies were in that original signal. So I'm going to plot my x and my theta here. So these are my results for 2 seconds. And here I'm plotting theta, although x would actually look exactly the same since they only differ by L, which is 1 in this case, but we desired theta. So at the top we have the forcing function operating at that 105 radians per second. It's a sine function, so it just keeps repeating itself. And then the bottom we see our result, that theta. And we can clearly see it's oscillating at 2 frequencies. Now this one we do not see beating in because we see the driving frequency was much larger than the natural frequency, 105 radians per second versus about 5.6. So it is outside that rule of thumb difference where we would see beating. But we see in our results here 2 frequencies present, and we'll see, well, it's the natural frequency and the driving frequency, which we would expect. Now this slower frequency, so we see this peak to peak here at the slower frequency, we often call the baseband frequency. So this slower wave here from this peak to this peak would be called the baseband frequency here. Now in this case that is also the natural frequency of this mechanical system. And then this shorter time period where we could do this peak to this peak about, that is going to be the carrier frequency. And in this mechanical example, that is the driving frequency. But these terms, baseband and carrier, are often used in electrical engineering, where we have some wave happening at these 2 frequencies. Now, I could calculate the time period between the peaks, but instead, I'm just going to look at the power spectral density and reconstruct what I know is the original signal. I know that it's oscillating at the natural frequency and the driving frequency. So let's just make sure we're getting those same results in the power spectral density. So I'll run the rest of this. I'm doing a discrete Fourier transform as I did previously, and then I'm going to plot the power versus the frequency to get the PSD. And this is what we get for our power spectral density. So the resolution of it is going to be determined by how long I sampled. I did this one arbitrarily for 2 seconds. I could have done it longer or shorter, but I'm pretending that it only took 2 seconds of data. And then the range of this that I can detect, that's determined by the time step. I did 0.01 seconds, but I could have changed that here. But I'm pretending like I just collected this data and I'm doing the analysis. So we see here 2 really nice peaks. We see one here at 103.7, and we see the first peak here at 6.283. Now, these are a little bit off from what we expect. We should see 105, since that was the driving frequency, and we see about 104, and the natural frequency was 5.6 about, and we see 6.2. But part of this is going to be caused by the resolution that I have. This is where kind of the closest it could find a peak based on my resolution, which was determined by that 2 seconds. So let's just see what happens. What if I sampled this for longer? Can I get closer to where these actual peaks should be? So going back into the code, here we go. Instead of doing it for 2 seconds, let me do it for 6 seconds. So we've sampled longer, and that's reflected here in the plot. We have more oscillations because we sampled longer, and we see the power spectral density here. We have a much sharper peak because our resolution is better. So let's see, by tripling how long we sampled, where we're getting. So we're at 104.7. That's closer than we were before to the 105, and the 105 itself is slightly rounded. And our first peak we're seeing at 5.23. Again, that also seems closer to the 5.6 that we expect. So one more time, I'll increase the time to 20 seconds just so I have even longer of sampling, and look at the power spectral density, and we should get even closer. So we see our second peak, the driving frequency, 104.6. We can actually double check to see how much that 105 was rounded. And we see our first frequency, 5.65. That is now really close to what we calculated to be the natural frequency. Again, that was rounded off too. So both of these, let's just check our driving frequency is being calculated here correctly. It is 104.7, so that 105 was rounded. And also the natural frequency we find here, when we calculate it correctly, 5.59. So that first one is still a little bit off, but those 2 peaks are pretty close to where we expect them to be. So final recap, we ended up with our theta of t using 2 different methods, although the basic procedure was exactly the same. The only difference was, did we change our coordinate to theta at the equation of motion step, or did we go through it with a more convenient equation, degree of freedom x, and then after we solved for x, then convert to the desired degree of freedom, theta. But both gave us the exact same results. It just depended where did we account for that coordinate transformation.